video click, so maybe it's time to start. Mikhail is ready. So would you share the screen?
Yes, I will do that.
Perfect. We see.
Great. So first, I'd just like to thank Professor Arzantsev and HSE for inviting me to speak. I'm currently a visiting researcher at Shamoon College of Engineering, and I'll be speaking about rigidity and rationality of Pham-Brieskorn Threefolds.
Maybe you can full screen format to change something on your computer to make the.
Do you see all? You see?
Yes, we do see all details.
All of my all the stuff at the bottom. All right, let me try this. If I just share the window, maybe. Is this better?
No, nothing changed.
Maybe Control L or something else.
Let me try. Maybe I can share it. Maybe I can try through Reader. Sorry. This is not better, eh?
No, nothing changed. But okay, so in any case, we see your screen. So if there are no more ideas how to change, we can do in this way.
Okay, so I will continue. Hopefully it's not too painful for you guys.
Okay.
So I'll speak about rigidity and rationality of Pham-Brieskorn Threefolds. So first, I'll give you the definition of a Pham-Brieskorn ring. So this ring, B, which I denote by B, A0, A1, all the way up to AN, is the quotient of a polynomial ring by the ideal generated by this element. So each of the generators is raised to some power, A0, A1 to AN, and this ring is called a Pham-Brieskorn ring. And for each I will let little xi denote the image of big xi in the Pham-Brieskorn ring, and I'll use that notation later. And so I was interested in the following two questions. For which n+1 tuples is the ring, this Pham-Brieskorn ring, rigid? And for which n+1 tuples is this ring rational? And so I need to tell you what it means for a ring to be rigid. So some definitions. So let B be a commutative ring. Derivation D from B to itself is locally nilpotent if for every element of the ring there exists some natural number such that if you apply D enough times, you eventually get to 0. And one of the simpler examples is when our ring is a polynomial ring. For any I, the partial derivative is a locally nilpotent derivation. And a ring is said to be rigid if the only locally nilpotent derivation from D to itself is the 0 derivation. And for those of you who are interested in GA actions on affine varieties, over characteristic 0, it's known that if B is a K-domain, then the spectrum of B is rigid, or you would say the spectrum of B is rigid if it admits no non-trivial GA actions, and that's because you have a bijection between the set of non-trivial GA actions and the set of non-trivial locally nilpotent derivations. So a conjecture which appears in Kaliman and Zeidenberg from the year 2000, and I don't know if it came up before then, but we see it there, is assume that n is at least 2 and that these exponents appear in increasing order, then the Pham-Brieskorn ring is not rigid if and only if A0 equals 1 or A0 equals A1 equals 2. And so here I've just stated the conjecture again, and I want to give you some remarks about it. So one direction is easy. So if A0 equals 1, then this Pham-Brieskorn ring is a polynomial ring, and that's not rigid. And if A0 equals A1 equals 2, then we can produce this isomorphism of rings from our Pham-Brieskorn ring to a ring R of this form. So R is equal to this ring. It's a polynomial ring quotiented by an ideal generated by x0, x1 plus this other term where this is the same term as before. And if we let D from R to itself be the derivation determined by its values on generators, where we set dx0 equals 0, dx1 to be equal to this sum, and dxi to be equal to x0 for every I, then it turns out that D is well-defined and locally nilpotent and non-zero, and so R is not rigid. And because R is isomorphic to this Pham-Brieskorn ring, the Pham-Brieskorn ring we started with is also not rigid. The other direction is harder. So to prove the other direction, we assume that the first entry is at least 2, and the second exponent is at least 3. So A0 and A1 are not both 2. And we want to prove that our Pham-Brieskorn ring is rigid. And in the n equals 2 case, so the 2-dimensional case, this was solved by Kaliman and Zeidenberg, lemma 4 of this paper. And we managed to prove the n equals 3 case. So it's solved by the results in this talk. And it's a combination of work from my PhD thesis together with joint work with Adrien Dubouloz. And as far as we know, the 4-dimensional and higher cases are open. So I'll stop here for a second. Any questions about the setting here, about Pham-Brieskorn rings or rigidity or anything like that?
Maybe there are any partial results for arbitrary n.
Yes, thank you. There are many. So for arbitrary n, there are many partial results. It's a good segue into the slide. So
I'm sorry, but maybe Sergey wanted to ask something, right?
Sorry, I can't see because let me open.
Oh, no, everything is clear. Yes, I know some partial results, but okay, the setting is very clear. Thank you.
Okay, so I'll just give a few comments about some partial results. It wouldn't surprise me if this list is not exhaustive. So as we mentioned before, Kaliman and Zeidenberg proved the 2-dimensional case. A paper by Freudenberg and Moser-Jocelyn from 2013, they study quasi-extensions of locally nilpotent derivations, and many cases of rigidity follow from their study of quasi-extensions. A paper by Daigle, Freudenberg, and Moser-Jocelyn from a few years later, and a joint paper with Daniel Daigle. We proved some other special cases as applications of locally nilpotent derivations on graded rings. These two papers are geometric papers by Cheltsov, Park, and Wan, and they are able to prove the 3333 case and the 2336 case, among others. And they use different techniques from what the algebraists use. Basically, they study anti-canonical polar cylinders in Del Pezzo surfaces, and they use a result of Kishimoto, Prokhorov, and Zeidenberg that compares anti-canonical polar cylinders with locally nilpotent derivations on affine cones. and they show that these two rings, or it follows that these two cases are rigid. And then more recently, Liu and Sun use algebraic techniques. I think they study Z-graded rings, and they also prove a bunch of cases in many dimensions. So lots of positive results. And one remark, which is one of the points that we make here, is that there wasn't a clear direction for how to prove this conjecture in general. So that's one of the things we'll offer today.
I'm sorry, it seems that it's known that if all the AI is very big, then it is rigid. It's result by Finston and Maubach. If 1 divided by i's, the sum is less than, I don't know.
1 over n minus 2, I think.
Yes, something.
Yes,
like
yes, thank you. I had forgotten about that one. Finston and Maubach. Thank you for that. Any other questions, or I can continue? Okay, I'll continue. So we need to define certain relations between tuples of positive integers. So we let S be an n+1 tuple, and for each index I, we let Si be that same tuple, but with the ith entry removed. And then we define L to be the LCM of all of these. And we define Li to be the LCM of that same tuple, but with the ith index removed. And then we can define the cotype of a tuple to be the number of indices such that this Li, the LCM, is different from the LCM that you started with. And for each tuple S, it follows that the cotype is between 0 and n+1. And so almost done with the notation. So if we have an n+1 tuple S, we define this term Gi of S to be the GCD of the entry at the ith index and the LCM of everything else. And with this terminology, we can compare some tuples. So we write that S is less than S prime at the ith index if these conditions hold. So the two tuples are the same everywhere except at the ith entry. And this GCD divides AI, which in turn divides AI prime. And we write that S is strictly less than S prime if it's less than or equal to it and not equal to it. So this is easiest to see with an example, and it will give you some more intuition than maybe just the definitions do. So we let S prime be this tuple, say 2, 3, 3, 12, and we start considering the various least common multiples. So the least common multiple of everything is 12. If we remove the 0th entry, the least common multiple is still 12. If we remove the first entry, it's still 12. If we remove the second entry, the LCM is 12. But if we remove the last entry, the LCM is 6. So there's one index where these LCMs are different. And so the cotype of this tuple is 1. If we let S be the tuple 2, 3, 3, 6, then the LCM of these 4 entries is 6. And no matter which index, or no matter which entry you remove, the LCM is still 6. So the cotype is 0. And it turns out that S is less than S prime at the third index. You can see here that if you omit the third index, these tuples are the same. You can compute that Gi of S prime is 6, AI is 6, and AI prime is 12. And so these two conditions are satisfied. And so we have this inequality. And basically what this allows us to do is to define a hierarchy of tuples where we say that one tuple is lower than another tuple. And this has implications for rigidity of Pham-Brieskorn rings. So here are the implications of that. So first, notation, in order to save myself a little bit of space, I write BS instead of B, A0, A1, A2, up to AN. And the lemma, which follows from the discussion, or the lemma which we want to prove, which we prove, which depends on the discussion before, is that if S prime is less than S, then if BS prime is rigid, so is BS. So if you have these two
sorry.
tuples, sorry, go ahead.
So each of these relations are partial orders, right?
It is a partial order, yes.
Okay, thank you.
Thank you. Good remark. So yeah, so if you have that one tuple is less than another tuple, if the Pham-Brieskorn ring associated to the lower tuple is rigid, it follows that the Pham-Brieskorn ring associated to the higher tuple is rigid. And so here's the example using the tuples we used before. Since 2, 3, 3, 6 is less than 2, 3, 3, 12, the lemma implies that if B2, 3, 3, 6 is rigid, then so is B2, 3, 3, 12. And a consequence of this lemma is the following proposition, which allows us to reduce our conjecture to one of two cases. So we can always reduce either to the case of smaller dimension or to the cotype 0 cases. So the claim is that if the conjecture is true in dimension n-1, and it is true for the cotype 0 cases in dimension n, then it is true in dimension n. So I will give you the sketch of this proof, omitting some details, but at least you'll have the idea of what's happening. So here's a sketch. Assume the conjecture holds in dimension n-1, and assume it holds also for the cotype 0 cases in dimension n. And we let gamma n be this set of tuples. So the set of tuples such that no AI equals 1 and no pair of distinct AI AJ equal 2. And our goal is to show that if S is in gamma n, then the associated Pham-Brieskorn ring is rigid. So if the cotype is already 0, then there's nothing to prove because we assume that the conjecture holds for the cotype 0 cases. So otherwise, let's assume that our Pham-Brieskorn ring is not rigid, and we will derive a contradiction. So we let D be a non-zero locally nilpotent derivation, and we remark that there are two cases to consider. First, we consider the cases where the cotype is at least 2. And when the cotype is at least 2, we show that there exists an irreducible locally nilpotent derivation such that one of the generators, one of these xi's is in the kernel. And it follows that since D is irreducible, that the quotient by the ideal generated by xi is not rigid. And when you take this quotient, you obtain something that's isomorphic to another Pham-Brieskorn ring. And this Pham-Brieskorn ring, the exponents also satisfy that no pair equal 2 and none of them equals 1. But by assumption, this lower dimensional Pham-Brieskorn ring is rigid because we assume that our conjecture holds in dimension n-1. And so this is impossible. So this shows that we cannot possibly have that the cotype is at least 2. So the other case to consider is the case where the cotype is 1. And using that our Pham-Brieskorn ring is not rigid, we show that we can find some other tuple, T, which depends on the original one, such that the following two conditions hold. So the cotype is still 1, and the Pham-Brieskorn ring BT is also not rigid. And there exists some T prime, which is less than T, such that the cotype of T prime is 0, and T prime is also an element of gamma n. And by assumption, then it follows that T prime is rigid because the cotype of T prime is 0, and we assumed that our conjecture holds for the cotype 0 cases. And by the lemma, it follows that BT must be rigid. So I'll go back to the lemma here. Remember, T prime is less than T, and BT prime is rigid, so BT must be rigid. Sorry. And so on the one hand, we have that BT is not rigid by part 1. And on the other hand, we have that BT is rigid by the lemma, which is a contradiction to part 1 that we showed before. So this proposition shows that we can reduce to these special cases, the cotype 0 cases. So an immediate corollary is that since we know the conjecture is true for n equal 2, to prove the n equals 3 case of the conjecture, it suffices to prove the cotype 0 cases. And that's what our previous reduction shows. So any questions about the reduction to the cotype 0 cases?
Oh, it's very interesting how you prove that if cotype is not less than 2, then there is a variable in the kernel, or it's difficult to understand here.
I don't think it's so difficult. So I think it's a result of, if I remember correctly, it's a result of Day, Freudenberg, and Moser-Jocelyn, that if you have the cotype to be 2 or larger, then you can show that 2 of the generators are either elements of the kernel or local slices. And then I think it follows when you look at the properties of the grading of the graded ring, that you can show that at least one of them must be in the kernel. I think that's the general idea, but I have to check.
Okay, thank you. Yes,
exactly what's going on, but that's the general idea.
Yes, I understand. Thank you.
No problem. Okay. So a remark. So whenever we have a tuple like this, we can view this element, which is an element of our polynomial ring. So this element is a homogeneous element of degree L in this graded polynomial ring, where the weights are defined to be L over AI. Remember, L is the LCM of the exponents here. And so our Pham-Brieskorn ring can be viewed as an n-graded ring where the degrees of the generators are these WIs, which are equal to L over the L over the AI. And then it makes sense to consider the proj of this graded ring, which in turn is a closed subvariety of this weighted projective space. And proposition, the following are equivalent. So the cotype is 0 if and only if the proj of this graded ring is a well-formed quasi-smooth weighted hypersurface in weighted projective space. So for those of you who haven't seen quasi-smooth, well-formed weighted hypersurfaces before, I'll just tell you quickly what this means. So this proj of this is quasi-smooth, or more generally, the proj of a graded ring is quasi-smooth if the only singular point of spec of the spec of B A0 up to AN, the only singular point can be at the origin. So if it's non-singular everywhere but the origin, then we say that proj of this is quasi-smooth. And being well-formed is basically a condition on how this projective variety intersects the singular points of the ambient weighted projective space. And so for something to be well-formed, what it means is first, the ambient weighted projective space is well-formed, and that's a condition on the weights. And it also means that when you intersect your weighted projective variety with the singular points of your weighted projective space, that intersection has codimension at least 2 in the variety itself. So basically the singular points of P, when you intersect it with a variety, is not a big set. It's a small subset of your variety. So I need to talk briefly about Q divisors and cylinders. So let X be a normal projective variety. A Q divisor is a sum of this form. So where each CI is a prime divisor and each AI is a positive rational number. And we say that two Q divisors are linearly equivalent if there exists a natural number such that ND and ND prime are linearly equivalent integral divisors. And if X is a normal projective variety, an open subset is called a cylinder if U is isomorphic to a product of an affine line with some other affine variety Z. And finally, if we let H be a Q divisor, a cylinder is H polar if U is the complement of the support of some Q Cartier Q divisor D, such that D is Q equivalent to a multiple of H. Now, maybe there's kind of a lot here to digest if you haven't seen this before, but it's not too hard to see what's going on once you play with examples a little bit. So I'll give an example here with some pictures, which I find sometimes helps. So we let H be our Q divisor. I chose the Q divisor 2L0 minus 1/2 L1. My ambient space is P2. And so basically I'm taking two distinct lines and I let H be 2 times one line minus 1/2 times some other line. Then 2H is equal to 4L0 minus L1. And this is actually linearly equivalent to 3 times L0. And this divisor here is effective, which is what we were trying to achieve. And if we look at P2 minus the support of our effective divisor, we find that this is isomorphic to an affine plane. And so U is the complement of our surface S minus the support of our effective divisor. And since this effective thing was Q equivalent to some multiple of H, it follows that U is an H polar cylinder. So we have some divisor here, which may look nothing like what we end up with in the end. We found something that was equivalent to some multiple of it, and then the complement is then an H polar cylinder. So that's a simple example, and we'll see how this is useful for us later when we look at polar cylinders in certain Del Pezzo surfaces. So now I want to tell you about a theorem which was originally proved by Kishimoto, Prokhorov, and Zeidenberg about 15 years ago. And this is really nice because it compares the rigidity of a graded ring B with cylinders in Proj B. So we assume that that B is a graded ring of transcendence degree 2 over B0. So in our case, B0 is just the base field C. And we assume our ring is normal, finitely generated, and a domain. And we assume that it's saturated in codimension 1. So this is an algebraic condition which we don't really need to go into it, but it's a nice algebraic condition for prime ideals in graded rings. Let X be equal to Proj B and let H be an ample Q divisor such that we have this isomorphism here. Then the graded ring B is not rigid if and only if X contains an H polar cylinder. And I just want to give a remark about this. So this isomorphism, the fact that such an H exists is a theorem of de Maizière's, and this is often called the DPD construction. DPD stands for de Maizière, Pinkham, and Dolgachev. But if you didn't know it in advance, it's not obvious that such an isomorphism exists. But their result basically makes this connection between graded rings and the cylinders in the corresponding projective variety. And it turns out that for Pham-Brieskorn rings, a Pham-Brieskorn ring is saturated in codimension 1 if and only if the cotype of this tuple is 0. And using this fact with a little bit of work and using a result of Dolgachev, it's sort of an adjunction formula result. We obtain the following corollary. So let B be a Pham-Brieskorn ring of cotype 0, and let alpha denote this quantity. So this quantity is the degree of the element, the sum of the xi's. So the degree of that polynomial minus the sum of the weights. So this is called the amplitude of our weighted projective hypersurface. Then it turns out that we have this isomorphism of sheaves. So this isomorphism here, and this is where we use Dolgachev. And the following three things are true. So if alpha is positive, so the amplitude is positive, then the canonical divisor is ample, and B is rigid if and only if X doesn't contain a canonical polar cylinder. If alpha is 0, the canonical divisor is trivial, and X is not even birationally ruled. And so in particular, X doesn't contain a cylinder, and so B is necessarily rigid. And finally, if alpha is negative, the anti-canonical divisor is ample, and B is rigid if and only if X doesn't contain an anti-canonical polar cylinder. So before I go and apply this to the case where n equals 3, any questions about any of this? So the cylinder stuff, or the isomorphism of sheaves, or this equivalence by Kishimoto, Prokhorov, and Zeidenberg. Any questions about any of this stuff?
Maybe a question about the future. So you will really apply this cylinder technique to get results on the rigidity of these varieties, right?
Exactly. So we'll see soon that a lot of the work is actually, well, a good chunk of the work is already done for us. And for whatever's left over, we managed to do it ourselves. And we used this result to get the rigidity of the cases that we're missing. Any other questions?
Excuse me, may I ask you to make the presentation bigger? If you click on the right, no, on the very right, there are 3 dots on the gray background.
I don't see
Yes,
those three dots.
is this the menu? Yes, just a bit right, a bit to the right. There is a bit to down, a bit down. Yeah, this one. Click this 3 points. There is option present.
Oh, wow.
This to work.
That's what we needed.
Yes, thank you very much. Yeah.
Thank you. That helps a lot. Okay, so I'll continue. So basically, I just restated the corollary in the n equals 3 case. So nothing new here. I just plugged in n equals 3, and now I'll give you some remarks about the n equals 3 case. So when alpha is greater than 0. So when alpha is greater than 0, Cheltsov, Park, and Wan, they proved that a normal rational surface with quotient singularities and ample canonical divisor can't contain a cylinder. And essentially the same proof goes through without the assumption of rationality. So since X cannot contain a cylinder, the right-hand side of part A is satisfied. And so in this case, these Pham-Brieskorn rings are rigid. Oh, I'm sorry. When alpha equals 0, we already showed that X is not birationally ruled, proj B is not birationally ruled, so it doesn't contain a cylinder, so B is rigid. And so it remains to prove that for A0, A1, A2, A3, and gamma 3, that if the amplitude is negative, then X doesn't contain an anti-canonical polar cylinder. Let me tell you what gamma 3 is. If you remember before, gamma 3 is the set of tuples such that none of them is equal to, none of the entries is equal to 1, or no two among them equal 2. So yeah, so here, recall gamma 3 is the set of tuples such that no AI equals 1 and no pair equal 2. And so a proposition, let B be a Pham-Brieskorn ring such that the cotype is 0, and this tuple is an element of gamma 3. If alpha is negative, so the amplitude is negative, then there are only 8 possible cases. Alpha, A0, A1, A2, A3 is one of these 8 cases. And the proof is one paragraph of elementary number theory. So we only now have to worry about these 8 cases. And 4 of these cases are essentially solved for us once we compute the self-intersection number of the canonical divisor and the singular points of the proj of these Pham-Brieskorn rings. So here's the theorem. This is a classification of Del Pezzo surfaces with Duval singularities that do and don't admit any anti-canonical polar cylinders. So if S is a Del Pezzo surface of degree D with Duval singularities, then S doesn't admit an anti-canonical polar cylinder if and only if one of the following hold. So the degree is 1, and either S is smooth or allows singular points of these types. D equals 2, and S is smooth or allows singular points of type A1, or D equals 3, and S is smooth. And in all other cases, our Del Pezzo surface, if it has at most Duval singularities, will admit an anti-canonical polar cylinder. So this theorem, after we compute the self-intersection number of the canonical divisor and the singularity types of the proj of these guys, gives us the 4 middle cases, the 3, 3, 3, 3, 2, 3, 6, 6, 2, 4, 4, 4, and 2, 3, 3, 6. These first 2 cases follow from another result, I believe due to Cheltsov, Park, and Shramov, who proved something stronger. So they prove that the proj of B3355 has a large log canonical threshold, and that's a stronger condition than the cone than containing an anti-canonical polar cylinder. So their results actually imply that B3355 and B3344, the proj of those don't contain anti-canonical polar cylinders, and those are rigid as well. But I don't really want to get into log canonical thresholds, but just to say that that work has already been done for us. But there are two cases that remain that don't fall under previous work. And the reason is that their log canonical thresholds are small and they don't admit Duval singularities. So I will talk about the 23530 case. And the ideas are similar for the 23412 case, and just to not have to do the same thing twice, I will show you the 23530 case. So we want to show that this surface doesn't contain an anti-canonical polar cylinder. And the way we do that is we show that if it does contain an anti-canonical polar cylinder, then there exists a smooth degree 1 del Pezzo surface S hat that also contains an anti-canonical polar cylinder. And since we know that this is impossible by Cheltsov, Park, and Wan's classification, we conclude that our assumption that S contains an anti-canonical polar cylinder could not have been correct. So that's the strategy of the proof. So some facts about our surface S. S has 3 singular points, P2, P3, P5, and I label them in this way because they're of type 1/2, 1, 1, 1/3, 1, 1, and 1/5, 1, 1. So these are cyclic quotient singularities, but they're only the first one is Duval. These last two are not Duval. And we have this curve delta, which we define to be the 0 set of the element x3 in S. And it turns out that delta is isomorphic to a projective line. And each of these singular points lie on delta with multiplicity 1. So the picture looks like this. We have our projective line delta passing through each of the 3 singular points. And I'll tell you about these curves and this U in a minute. So a lemma, let S be our surface. If S contains an anti-canonical polar cylinder, U, and U is the complement of the support of some divisor that is Q equivalent to our anti-canonical divisor, then delta is contained in the support of D. So basically what this is saying is the complement of our anti-canonical polar cylinder contains this curve. The support of the complement contains this curve delta. So what do we do? So we know that delta is contained in the support of D, and now we resolve the singularities. So we let sigma be the minimal resolution of singularities. So we blow up these 3 singular points. And because we know the types of these singular points, they're 1, 2, 1, 1, 1, 3, 1, 1, and 1, 5, 1, 1 singularities, the exceptional curve over that singular point is a projective line for each of those 3 singular points. And it turns out that this divisor here, D prime, if we let D prime be equal to sigma upper star of D plus these discrepancies, then D prime is effective. It contains these 3 exceptional curves and delta tilde in its support, and it's Q equivalent to an anti-canonical divisor of S tilde. So you can see this because sigma upper star D is effective because D is effective, and it contains these 3 curves in its support because each of our singular points lie along delta, which is contained in the support of D, and we're only adding positive multiples of these exceptional curves here. And so each of these 4 curves is a projective line. And when we look at the inverse image of our cylinder U in S, we find that the complement of the support of D prime in S prime is an anti-canonical polar cylinder in smooth surface S tilde. So again, a lot to digest here. Let me show you a picture. So here's the picture. Assume U is an anti-canonical polar cylinder. We know that delta is contained in the support of the complement. Suppose we have some other curves in the support. So I just put two curves here, but there could be many others. Let's say there's only these two. When we blow up the singular points, we get that everything here is in the support of the complement. So we have delta tilde, the three exceptional curves, and the strict transforms of the other curves that came from here in the complement. So sigma inverse U now is an anti-canonical polar cylinder. And what we're going to do now is we're going to start contracting curves.
Excuse me?
Yeah.
Yeah. May I ask you, how do we see that this is actually a cylinder? That it is A1 times something. How do we see fibers?
I assume that S contains a cylinder to begin with.
Okay, thank you.
And I take the comp and since it's anti-canonically polarized, I know that there is a divisor in the complement. Sorry, I know the complement is a Q divisor that's Q equivalent to an anti-canonical divisor. So I'm saying let this be the support of such a divisor. It's okay?
Yeah, thank you.
Okay, so as I mentioned before, after checking the self-intersection numbers, it turns out we can contract these three curves. And we'll let tau be this contraction. And since D prime is an anti-canonical divisor on S tilde, when we take the image of this divisor after contracting a bunch of curves, we find a cylinder in an anti-canonical polar cylinder in S hat. And again, I'll show you a picture of this. So we'll find that S hat contains an anti-canonical polar cylinder, but it can be checked that S hat is a smooth del Pezzo surface of degree 1. And this contradicts the Chaltsov-Park and Wan's classification of anti-canonical polar cylinders in del Pezzo surfaces. So here's the picture. We had this picture before. We have an anti-canonical polar cylinder in S tilde. So the first thing we do is we contract this -1 curve delta tilde, and we get this configuration of curves. So we have these three curves that now meet at a single point, plus whatever was left over, the other curves in the complement of the cylinder. We then contract our -1 curve here, and we get this configuration of curves. And then we contract the -1 curve one more time, and we get this configuration of curves. And since we had an anti-canonical polar cylinder all the way on the left, what's left over here is an anti-canonical polar cylinder, since we're just contracting curves on the boundary, in the complement of our cylinder. And after you compute what S hat is, you find that S hat is indeed a smooth del Pezzo surface of degree 1. And so our initial assumption that S contains an anti-canonical polar cylinder could not be true. So that's how we conclude that proj of our Pham-Brieskorn ring in the 23530 case doesn't contain an anti-canonical polar cylinder. And so we conclude that B23530 is rigid. And for the 23412 case, the proof is very similar. It's a little bit harder, but the idea is essentially the same. And so we conclude that these last two cases also don't contain anti-canonical polar cylinders. And so the technique is, I just call it reduction to Chaltsov-Park and Wan. And so we conclude that this Pham-Brieskorn threefold is not rigid if and only if A0 equals 1 or A0 equals A1 equals 2. So that concludes the portion on rigidity. Any questions about any of this? Say, starting from here. Okay, so so if that's okay with everybody, I'll move on to rationality. So Professor Gurjar was an examiner of my PhD thesis, and he asked me the following question. So for which four tuples A0 to A3, A0, A1, A2, A3 is spec of this Pham-Brieskorn ring rational? And I didn't know how to prove this, and so I worked on it, and in the end, we can do it. So here's how. So we start with a lemma. So the spec of a Pham-Brieskorn threefold is rational if and only if the proj of that graded ring is rational. And so here's the proof. Let B be a Pham-Brieskorn ring, and let X be the proj of that ring. So if X is rational with function field K, then the function field of spec of B is purely transcendental of transcendence degree 1 over our over something that's already purely transcendental of degree 2. And so it follows that it's purely transcendental of degree 3 over C, which is rational. Conversely, if spec B is rational, then proj B is stably rational and two-dimensional. And it's a consequence of Castelnuovo's theorem that stable rationality in dimension 2 implies rationality. So instead of answering the question for which tuples is spec B rational, we can answer the question for which tuples is proj B rational. So that's what we're going to do. And again, we will reduce to the cotype 0 cases. So this is true actually in any dimension. Let B be a Pham-Brieskorn ring, and there exists some other Pham-Brieskorn ring such that the cotype of the second one is 0, and the proj of those two rings are isomorphic. So here's the sketch of the proof. So let S prime be an n+1 tuple. If the cotype is 0, we're done. So otherwise, we show that there exists some other tuple S and some index I such that S is less than S prime, and the cotype of S is less than the cotype of S prime. And then we can use the fact that if S is less than or equal to S prime for some index I, then one Pham-Brieskorn ring is a Veronese subring of the other for some natural number D. And in this case, since BS is isomorphic to BS prime, the Veronese subring of BS prime, it's clear that we have the first isomorphism because these two rings are isomorphic, so their projes are isomorphic. And in general, when you have a Veronese subring, the proj of a ring is isomorphic to the proj of its Veronese subring. And so we obtain the second isomorphism. And so we found another Pham-Brieskorn ring of cotype 1 lower, such that the proj of that thing is isomorphic to the proj of the Pham-Brieskorn ring we started with. And we repeat this argument multiple times until the final Pham-Brieskorn ring we obtain has cotype 0. So in this way, we can reduce our question further. We can reduce our question to the cotype 0 cases. So here's an example of us doing this in practice. So when is B10334 rational? So 10334 is greater than 2334, which in turn is greater than 2332. And so to determine whether B10334 or spec B10334 is rational, it suffices to determine whether proj B10334 is rational by the first lemma. And this is isomorphic to this, which in turn is isomorphic to this. And so it suffices to determine whether proj 2332 is rational. And so in this way, we can always do this. And in this way, we've reduced our rationality question to the following one. Suppose the cotype is 0, when is the proj of this ring rational? So any questions about the reduction here?
I have a question not about the reduction, but about this general lemma. Can you return 2 slides? This one. No.
Yes.
No, not this one, but lemma here. I think that this lemma has nothing to do with this concrete variety. It looks like a general fact. So
Very general.
if you take a proj of some graded algebra and its spec, then it seems that one is rational if and only if the other is rational.
In dimension, if proj is that is 2-dimensional.
And in any dimension?
No, I don't think so, because stable rationality doesn't imply rationality in general, right?
No, but my arguments may be as follows. You have a projective variety and you have a affine cone over this variety.
Yeah.
And your projective variety is a geometric quotient by action of C star on the affine cone. And then you can apply Hilbert's theorem 90 that birationally on the open subset, your affine cone is just a direct product of one-dimensional torus and the projective variety downstairs. And when you multiply directly by one-dimensional torus, it doesn't change rationality. Torus action are birationally trivial. This is Hilbert's theorem 90. But maybe
I suppose I believe you, but I'm really not.
So
sure.
the question is, if something times a1 is rational, does it apply if this something is rational? So we don't know it anymore.
This is a question of stable rationality, and this may be a problem. I see. Okay.
Yeah. So here I'm just using a very special case, but in 2 dimensions, it's generally true. But
the property to be unirational is equivalent, but rational is more delicate property. I see. Sorry.
Any other questions? Okay. So we've reduced the question to the cotype 0 cases. And again, we use similar ideas. So we assume that B is our Pham-Brieskorn threefold of cotype 0, and we let alpha be this amplitude again, and we let X be equal to proj B. Then once again, we have this isomorphism of sheaves. And so there's 2 comments. If alpha is negative, the anti-canonical divisor is ample, and X is a singular del Pezzo surface with quotient singularities. And in this case, it's known that X is rational. So we don't have anything to do here. The hard work is done for us. And when alpha equals 0, the canonical divisor is trivial, X is not birationally ruled, and so X is not rational. So it suffices to answer the following question. We need only consider the positive amplitude cases. So suppose the cotype is 0 and the amplitude is positive. When is proj of B rational? So since X is quasi-smooth and well-formed, theorem of Dolgachev tells us that the dimension of the second cohomology group is equal to the dimension as a vector space of this component, the degree alpha component of the graded ring. And since a necessary condition for X to be rational is that H2 is 0, we must also have that the dimension of this alpha component is 0. And the theorem, which I managed to prove, is let B be a Pham-Brieskorn ring and let X equal proj B. Suppose the cotype is 0 and that the AIs are written in increasing order and alpha has positive amplitude, then the dimension is 0 if and only if A0 equals A1, A2 equals A3, and the GCD of A0 and A2 equals 1. So, so basically, this condition, when the amplitude is positive, is very rare. And this result is a corollary of a general result that I prove on numerical semigroups. And unfortunately, the proof is long, but it only uses just elementary number theory like. Oh, so there's a little bit of a glitch there, but so we've basically reduced our problem to very few cases. When cotype is 0, amplitude is positive, the only remaining cases to consider are the proj of these cases where the GCD of A0 and A2 equals 1. Because when this is not the case, our second cohomology group is the dimension of the second cohomology group is non-zero, and X is not rational. Oh, sorry. Okay. So as I said, the only remaining cases to consider are these ones. And it will turn out in view of the following proposition that these cases are indeed rational. So here's the proposition. Let A and C be positive natural numbers and consider the following graded polynomial ring. So all of the xi here are homogeneous of degree C, and all of the yj's are homogeneous of degree A. And suppose that f can be written as a sum, where g is some function in the xi's, h is some function in the yj's, and their sum is irreducible, homogeneous of degree L. And both g and h are non-zero. Then the following thing is rational. Proj of R mod f is rational over K. So that's my claim. And here's once again, a sketch of the proof. There are things that need to be checked, but regrading if necessary, we can assume that the GCD of A and C is 1. And we let B be our graded ring. And we define the following elements of the function field K of proj B. So we let Ti be all of these fractions. So x1 over xk, x2 over xk, x3 over xk, all the way up to k minus 1. Then we do the same thing for the y's. So we consider y1 over yl, y2 over yl, y3 over yl, all the way up to l minus 1. And this special element u, which is xk to the a over yl to the c. And this all makes sense because these TIs all have degree 0 because xi and xk have the same degree. Same thing for the yj over yl. And since xk has degree c, the numerator here has degree ac, and the denominator here has degree ac. And so this too is an element of degree 0. So it makes sense. These guys are actually elements of the function field of proj B. And then the next step is to show that the degree 0 subring of the localization at this element yl is contained in the subfield generated by these elements, which in turn is contained in the function field k. And the next step is, since the spectrum of this thing is an open subset of proj B, the fraction field of that ring itself is equal to k. We're just taking the fraction field everywhere here. And since the stuff on the left, the field on the left is equal to the field on the right, it follows that k is equal to the field generated by these elements. And if you count them, there are k plus L minus 1 elements. And since the transcendence degree is k plus L minus 2, we need only show that this element u can be expressed, we need only show that u is an element of the subfield generated by the other elements. So we will go ahead and do that. We use the fact that the GCD of AC equals 1 together with the fact that f equals 0 in frac B to write u in terms of the TI and the VJ. And so it follows that K is actually generated by K plus L minus 2 elements. And in fact, these are them. And it follows that that K is purely transcendental over K. Sorry, there's a mistake here. This should say K and not C. This is actually true over any field. And so if we apply the previous proposition to the A0, A0, A2, A2 cases, basically we take G to be equal to this guy and H to be equal to this guy, we conclude the following. Suppose we write the exponents in increasing order and the cotype is 0, then the proj of our graded ring is rational if and only if one of the following hold. A0 equals A1, A2 equals A3, and the GCD is 1, or the amplitude is negative, in which case we have the del Petzl surface. And so, so we've managed to answer Professor Gurjar's question. And that's the end of my talk. Here are some references, and I can share this with anyone who was interested. Any questions about the rationality part?
So do you know the way how to reduce dimension when we consider rationality?
I'm sorry?
Well, when you told us about rigidity, you reduced to a three-dimensional case, yes?
I reduced the dimension n case to the dimension n-1 case.
Yes, and can you do the same in case of rationality?
I don't know how the arguments would work. Because really I'm really using the fact that everything here is two-dimensional. I'm not actually making a reduction in dimension here. I'm just computing stuff about surfaces.
Okay, thank you.
So I don't know how, yeah, I don't know how that could work. But maybe it's worth noting that some of this stuff actually works in higher dimension. If you're interested just in checking certain things, for example, this works in any dimension. You can find lots of examples. This type of argument, sorry, the type of argument here, the cohomology argument, also works in higher dimensions. So you can find obstructions to rationality there, but I don't know how to deal with families in higher dimensions, with the whole family, let's say.
I have a short comment concerning this part.
Sure.
I don't remember, maybe I sent you our paper where we study rationality of trinomial hypersurfaces and trinomial variety in general, because I see here darkly some analogy with this case, even in your proof.
Okay.
Have you seen it? You have a polynomial with 3 terms, and variables are different in different terms. This is called polynomial.
Okay.
And we have also some numerical condition for such a hypersurface to be rational.
Okay.
Didn't you see our proof? No.
I know you sent it to me, and I took a brief look at it, but I didn't look at it in detail enough to be able to make a comment about analogies between the two, unfortunately.
Okay. So, dear colleagues, any more questions?
I'm sorry. Can I get the slides and references? Can you send it to the chat, for example?
Yeah, sure. I don't mind. I don't mind sending it to you. Just send me an email, and I'll gladly send it to you. I'll post my email in the Zoom right now. So, shoot. Chat.
And then maybe I have a request, because I see that among participants of today's seminar, we have Ananya Pal and Nina Gupta. And I know that colleagues have a paper on arXiv with very similar title, and it was not mentioned. So maybe you may comment what are connection of your work with the work of Michael, which was just represented.
It seems that positive characteristic in their work.
Ah, so the difference is that this is in characteristic 0, right?
No, our result is for n equal to 2, not none. There is not much for n equal to 3. So, but that is arbitrary characteristic. And when we deal with arbitrary characteristic, some interesting things also happen. So we don't, our results are not so neat. Like there are cases where it's not this AIs are not necessarily 2 bigger than 2, but multiple of P. P is a characteristic, and the ring is not rigid. So those cases come up. Am I audible?
Yep.
Sure.
And Michael, do you know this paper by Gupta and Paul?
I actually just saw it on the archive today for the first time.
I see.
So I know of it, but I don't know it.
Yeah, we will be interested in your work. So if possible, you can, we will write to you for the slides.
Yeah, please do. Please do. I can also refer you to the papers. A lot of the stuff that we do for Pham-Brieskorn, well, the rationality arguments for Pham-Brieskorn actually work for many different hypersurfaces, and so it doesn't only apply for the rationality arguments don't only apply for Pham-Brieskorn Threefolds. It was just motivated by that question of Gurjar.
Yeah, means and another interesting question is, maybe I don't know, that may be difficult. Yeah, this unirationality. So I think they are unirational. Is it? That's so not always, right? Yes. If something is not unirational, it has to be rigid. That's a slice here. Huh?
Is that
unidimensional
always? No. Okay, so in low dimension, I guess yes, but in high dimension too? In high dimension also?
What's the question?
Well, you said if the proj is not unirational, then the cone must be rigid?
Not proj, I'm talking about the variety.
Oh, okay, so spec.
Yeah.
Okay.
That is just a slice theorem. If something is not unirational, it has to be a ruled cylinder. So I'm thinking that may be a approach to attack such problems, like to identify when they are unirational or not.
Okay, dear colleagues, if there are no more questions and comments.
I have one question about rigidity. It turns out that this hypersurface is either rigid or flexible, because when A0 is 1, it's just a affine space, and if you have two AIs equal to 2, this is just suspension over affine space. But is there some simple argument that this hypersurface is either flexible or rigid or just after all of this we can see it?
I'm sorry, Michael, do you know such a notion, flexible variety?
No, I don't.
Ah, okay. Mm,
Sergey, maybe you can explain briefly.
I try. Rigid, it means that there is no local nilpotent derivation, there is no GA actions, and flexible means that there are plenty of LNDs such that in any regular point, the tangent vectors to orbits of GA actions span all the tangent space. But maybe if you didn't think about flexibility, then there is no reason.
There's no reason why I would know the answer off the top of my head, I suppose.
Okay, thank you.
But maybe I should comment, Michael, because this is really a strange result. You cannot have few LNDs. You have either no LNDs, and this is rigid, or you have many LNDs, too many. You can move in any direction by orbits of GA actions.
In dimension 3.
Yes,
If the conjecture is true, then in any dimension. Can you go to the slide
okay.
with the conjecture, with the original conjecture?
Okay, okay. Huh.
so you have just one orbit of automorphism group in regular locals.
Mm-hmm.
Here it is. So the conjecture says that either you have first exponent equal to 1, Sergey, and why it is flexible in this case?
It's
Because it's just a
polynomial
finite space.
Because this is
polynomial
just a
ring.
fine space, I'm sorry. So this is a trivial case. And in the second possibility, when you have two exponent equal to 1, then this is a suspension over some other variety, over a fine space, in fact, right? And this is again flexible, I see.
There is a case when it is not flexible and it is not rigid if you allow not all the variables occur in this equation. So if you have some x0 cubed plus x1 cubed, but you have 10 variables, then it is not flexible and it's not rigid. But in this case, you have all of variables in the equation.
This is just you take a cylinder of a rigid variety, and you can move in the A1 directions and no in the rigid direction, something like this.
I would like to add, if I may, that this alternative, flexible or rigid, also holds for cones over cubic surfaces. If we take not any polarization of a cubic surface, then it is either rigid or generically flexible, almost flexible. So this is some interesting fact, holds in many cases, it seems.
Okay, so if there are no more questions and comments, then let me thank Michael for his nice talk. So indeed, beautiful subject, deep algebra, deep geometry, such a nice interplay and very detailed presentation. So everything was clear and very interesting results.
So thank you very much for having me, and thanks to all of you for joining. I wish you a great evening to everybody.
So this is task for all of us to prove this very nice conjecture. It should be proved in complete generality. So let us think about this.
Amazing.
Okay. See you, dear colleagues. Thank you very much for being with us.
Thank you.
Thank you.
Very nice talk.
Thank you.
Yeah.